NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will build an intuitive visual algorithm to solve equations of the form log base f of x of capital A equals log base g of x of capital A. We will extract the domain conditions and the core idea that makes the equation solvable. Start with the template. We consider log base f of x of capital A equals log base g of x of capital A. For any logarithm to be defined, the argument must be positive, so capital A is strictly greater than 0. Now, recall the base conditions for a logarithm. The base must be positive and different from 1. We'll apply these to f of x and to g of x separately. Here is the algorithm exactly as we will use it. The equation is equivalent to either of these systems. Option 1. Enforce conditions on f of x, and then set f of x equal to g of x. Option 2. Enforce conditions on g of x, and then set f of x equal to g of x. Both systems are completely equivalent. Why is this true? Because if the logs are equal to the same number t, then f of x to the t equals a, and g of x to the t equals a. Therefore, f of x must equal g of x, provided the bases are valid. That is the heart of the method. Let us lock in the idea with a short example. Solve for x. Log base x plus 2 of 5 equals log base 3x minus 1 of 5. First, write the domain constraints. 5 is positive. The base x plus 2 must be positive and not equal to 1. The base 3x minus 1 must be positive and not equal to 1. Next, set the bases equal x plus 2 equals 3x minus 1. Solve for x, and then check the constraints. Now check the value 1.5 in the constraints. X plus 2 is 3.5 greater than 0 and not 1. 3x minus 1 is 3.5, also positive, and not 1. Therefore, all conditions are met. We conclude that x equals 1.5 is a valid solution. Summary. When log base f of x of a equals log base g of x of a with a positive, you may solve the simple equation f of x equals g of x, provided you also enforce the base conditions. The chosen base is positive and not equal to 1. That algorithm mirrors the exact structure we highlighted, and it works for all problems of this specific form. In this example, we will solve a logarithmic equation step by step and check the domain carefully. Here is the equation. Step 1. For a logarithm, the base must be positive and not equal to 1. We apply this to both bases. For the left base, 5 plus x over 3 is greater than 0, giving x greater than negative 5, and it cannot equal 1, giving x not equal to negative 2. For the right base, negative 1 over x plus 1 must be positive. So x plus 1 is negative, that is x less than negative 1, and the base cannot be 1, which again excludes x equals negative 2. Their intersection is the open interval from negative 5 to negative 1, excluding negative 2. Because both logarithms have the same argument 3 and are defined, we can equate the bases. 5 plus x over 3 equals negative 1 over x plus 1. Cross multiply and expand. We get open parenthesis x plus 1 close parenthesis times open parenthesis 5 plus x close parenthesis equals negative 3. Expanding gives x squared plus 6x plus 5 equals negative 3. Move everything to one side to get x squared plus 6x plus 8 equals 0. Factor the quadratic. It becomes open parenthesis x plus 2 close parenthesis times open parenthesis x plus 4 close parenthesis equals 0. So the potential solutions are x equals negative 2 and x equals negative 4. Now check against the domain. Negative 2 is excluded because it makes the base equal to 1 and also violates the interval. Negative 4 lies strictly between negative 5 and negative 1, so it is valid. The solution set is the singleton negative 4. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.